There are three broad categories of compound lipids: the phospholipids, sphingolipids, and glycolipids. And the big difference here is one of the fatty acids has been removed. We have a head group, or a phosphate, and then a head group on top of the phosphate. So the phospholipids, we have phosphatidic acids, phosphatidylcholines, and phosphatidylethanolamines. The phosphatidic acids, we just have a phosphate here. So it's a glycerol acid, a fatty acid, and phosphoric acid. It's an important intermediate in the synthesis of other phospholipids because you still have to add a head group to get a phosphatidylcholine, as we see here, or a phosphatidylethanolamine, which means we're just going to add ethanolamine or choline there, which we'll look at the structure in a second. So here we see choline. And this is an important part here. It's a quaternary ammonium with a positive plus here, which makes it useful for biological signaling. So the phosphatidylcholines, the lecithins, the glycerol esters of fatty acids, phosphoric acid, and choline. And these are synthesized in the liver and are present in nerve tissue. They're edible, they're digestible, and they can also be used as an emulsifier, which is a compound that can mix water and oil-based layers into one layer. Phosphatidylethanolamines. Here we see ethanolamine. This nitrogen has a positive charge just because in a biological solution, the pH of a biological cell is around 7, and the pKa of an ammonia group is more around 10, and so just because it's in a pH of 7, it gets protonated. And so in a biological solution, you'll typically see the negative charge here and the positive charge here because of the acidities of the solution that they're in. And these are oftentimes found in plasma membranes. Sphingolipids. Now we're adding sphingosine. You have both hydrophobic and hydrophilic character. And you form a group of compounds upon hydrolysis. We get a hydrophilic group, either phosphate and choline or carbohydrate, a long-chain fatty acid, and sphingosine, which is an unsaturated amino alcohol, which we see right here. It's different than an amino acid because if it was an amino acid, this would be a carboxylic acid group here, and it's not. You just have the alcohol group here. And glycolipids. These contain a carbohydrate group found mainly in cell membranes of brain and nerve tissues. And there's two important classes, the cerebrosides and the gangliosides. Notice the names make you think the brain, because cerebral is like brain, mental, and gangliosides, the ganglia, a lot of nerve tracts. And so here, cerebrosides contain either D-galactose or D-glucose, and we have this sugar along with the sphingosine molecule. And here we see gangliosides resemble cerebrosides but contain oligosaccharides instead of monosaccharides. So instead of just a D-galactose or a D-glucose, you'd actually have 2 to 6 monosaccharides linked together here in a ganglioside. So what is the classification of the following lipid? Notice your phosphate group and notice your ethanolamine. So this is a phospholipid, and more specifically, phosphatidylethanolamine. Here, we have a beta-galactocerebroside. So it's a glycolipid. Again, glyco for sugar, because you have this galactose here, and lipid for the sphingosine over here. So if we go back to our sphingolipids, we notice that the structure of sphingosine is kind of sort of similar to the structure of glycerol. And so again, sphingosine will come up a lot in biochemistry as a major biological compound when we talk about glycolipids. Steroids. Here we have 4 rings fused together. Notice 1, 2, 3, 4. These are synthesized in the liver as cholesterol, and the cholesterol is chemically modified to make things like testosterone or estrogen or progesterone or any other steroid hormone that we're utilizing here. So all steroids are very closely related in structure with these 4 fused rings. They are highly diverse in function. And so cholesterol is very different than progesterone. Cholesterol is the most abundant steroid in the body. It's widely distributed in cells. It's put into every plasma membrane to toughen it up because animals don't have cell walls. And therefore they need something to toughen up the plasma membrane so that it can withstand the normal forces of planet Earth. And therefore cholesterol is added to all plasma membranes. It's also, again, chemically modified into lots of different hormones, like in men, testosterone, and in women, estrogen, progesterone, and testosterone. Women produce testosterone in the adrenal cortex of their adrenaline gland, which is, even though it's all the adrenaline gland is actually 2 totally different organs. The adrenal medulla in the middle makes epinephrine and norepinephrine, whereas the adrenal cortex, now you're making your testosterone and your mineralocorticoid hormones, like aldosterone. So example of steroids, we have bile salts, which aid in the digestion of fats. Ergosterol, it's a yeast steroid. It's converted to vitamin D by ultraviolet radiation. And that's why people say you can get vitamin D from sunlight. However, that really only applies in the summer when we spend time outside and don't have a lot of clothes on and actually get a lot of sun exposure. If it's not very sunny outside or you're wearing clothes covering up your skin, then you're not getting enough ultraviolet radiation to produce vitamin D in the body. Digitalis and related drugs come from steroids. Adrenal cortex hormones, these are involved in the metabolism. And sex hormones like testosterone and estrogen come from steroids. So identify the functional groups in cortisone, again another steroid. You have a hydroxyl group, a carbonyl group, another hydroxyl group, another carbonyl group, another carbonyl group, and the double carbon bond. These are all the different functional groups that we see in this molecule. The hydrophobic nature of lipids has important biological consequences because they are not soluble in water. So lipids aggregating will cause atherosclerosis, the hardening of the arteries, as these lipids, the cholesterol especially, coats the arteries and it hardens up. And it can form biological membranes, like the plasma membrane, when lipids aggregate into the lipid bilayer. Atherosclerosis is a metabolic disease that leads to deposits of cholesterol and other lipids on the inner walls of the arteries. Blood pressure increases as the heart works harder to pump sufficient blood through the narrow passages, which may eventually lead to heart attack. Plaque formation begins because of a lipid's natural tendency to aggregate. Liposomes, these are complex lipids that are formed in aqueous mixtures, bounded by 2 layers of lipids. The hydrophobic alkyl chains are covered by hydrophilic groups on both of the liposomes inside and outside and have a water core. And so this kind of mimics the plasma membrane. You have the lipid bilayer and the hydrophilic portions are on the inside and the outside with the hydrophobic area throughout. And so this really mimics a baby plasma membrane with a liposome. Lipoproteins. Here we have proteins that move around cholesterol. This is when you hear the terms good cholesterol or bad cholesterol. There's really only one cholesterol. It's cholesterol. Good and bad deals with low density and high density lipoproteins. So, the low density lipoproteins here are putting your cholesterol into peripheral tissues. Your high-density lipoprotein is taking your cholesterol out of your peripheral tissues. And so basically we have an antagonism of one is taking cholesterol out of your arteries and packing them away, and one is putting them back into your arteries.